Hello YouTube. So in this video I'll be deriving the surface area, or rather the formula for the surface area of a sphere. So in a standard geometry class you'll probably have learned that the surface area of a sphere is 4 pi r squared, but you were never given an explanation for why. Well, in this video I will present a calculus based, derivation, not a proof, but a derivation for this formula. So to start off with, let me just present a few prerequisites that we need to know, some prerequisite information before we can proceed. So to create a sphere, we'll be, let's say we have a half circle on the x. So we draw an xy graph. Let's say we have a half circle like this of radius r. This radius r, the x and y graph. So in order to find the arc length of this, first of all, we're just drawing a half circle. To find the arc length, we can write this in terms of parametric equations. So we could start off with saying that x is equal to r cosine theta, or cosine t, not theta, and y is equal to r sine t, since that is the parametric equation for a circle. Okay, so in order to find the arc length of a function with two bounds, given the parametric equations, you have integral from a to b of the square root of dx dt squared plus dy dt squared times dt. And if you already watched my arc length video, then this should kind of make a bit of sense, because the dt over here cancels out with the dt's on the bottom, so you're just left with the integral, or the sums of all the different Pythagorean or dx dy's as you travel up through the curve. Okay, so basically we need to transform this into something that applies to a sphere. So this half circle, when revolved about the x-axis, it transforms into a sphere, obviously. So when you revolve this about the x-axis, you form a sphere. And then this equation, there's a derivation. It's really long and complicated, and I don't think I need to cover it, but a calc textbook will tell you. Oh wait, before we get to the surface area revolution stuff, we need to make sure we know our bounds. So our bounds are going to be 0 to pi. And the reason for that is because when we're going to be finding from this point to this point, so we know that at this point, well, x is at its maximum, so t has to be 0, obviously, and here x is at its minimum, so t has to be pi here, and it's kind of common sense, the lower and upper bounds. Okay, now we could get to the transfer or the revolution. So using Calc 2 techniques, which is really complicated and to cover in one video, you can transform this. So this is now revolved about the x-axis. So this is arc length. This is surface area. So there's a derivation for this, but I'm not going to cover it. Basically, you get a whole new formula of, you get 2 pi times f. It could be f of x, but in this case it's just y. Y as a function of t, so I guess y of t times the square root of dx dt squared plus dy dt squared dt. Okay, so how do we find dx dt, dy dt? Well, we could just differentiate these parametric equations in terms of t. So differentiating x, since r is a constant, we just get negative r sine t, and dy dt r cosine of t. Okay, so we can substitute this into our thing. So we get integral from 0 to pi of 2 pi times y of t. Y of t is just r sine t times the square root of this squared times this squared, so it's r squared sine squared t plus r squared cosine squared t dt. So sine squared plus cosine squared turn to just 1 as per the Pythagorean identity. So this expression just reduces to the square root of r squared, or just r. So what we're left with here is integral from 0 to 2 pi of r times these. So 2 pi r squared sine t dt. So now I can just erase. Let me just erase this on the top here. Oh wait, sorry. I put 2 pi up here. This should be pi. So now we have the integral from 0 pi 2 pi r squared sine t dt. And we could just take out the 2 pi r squared here and just take the integral from 0 to pi of sine t dt. That's equal to 2 pi r squared of negative cosine t pi to 0. And that's how we get 4 pi r squared, because this is equal to 1 minus negative 1, which is 2 times this. For more information on how to transform or find the formula for this arc length or for this surface of the revolution, you could probably consult a calculus textbook, but in this video I was just covering the basic steps for a derivation. Anyhow, thank you for watching, and I'll see you in a later video, I guess.